Okay, let's unpack this. Today, we are diving deep into the fundamentals of the Avi platform.
Hmm.
This is, well, it's a really critical piece of modern application delivery infrastructure, definitely moving the industry away from, static hardware load
All right,
balancers.
into that whole software-defined world.
Exactly. And our source material today, it's structured around a key certification exam.
Which actually gives us a great framework.
It does. It's like a high-value roadmap for the platform's core architecture and its operation.
Yeah, and that structure is exactly what we need. So our mission for you, the listener, is it's to go beyond just reciting facts for a test.
Right.
We're really extracting the fundamental architectural logic here, understanding those essential operational tasks, and pulling out the troubleshooting framework.
Okay.
It's a modern, highly elastic load balancing system we're talking about. Think of this as like your shortcut to understanding the why behind the platform, why it's designed this way.
And, while the source might be based on, I think it was 65 questions, something like that.
Yeah, standard technical certification format.
Right. But the concepts we're covering are, well, they're immediately applicable. Whether you're architecting a new cloud deployment or just trying to figure out, why your app is suddenly slow.
Absolutely.
We're really focusing on where the platform draws that line, the line between the intelligence and the actual workload. So let's jump straight into that demarcation line because it really defines the whole system, doesn't it?
It absolutely does.
Here's where it gets genuinely interesting. The Avi platform is architected around this really clear, non-negotiable separation.
Between the data plane and the control plane.
Yes, that's
Like,
its fundamental genius, I think.
completely agree. And we should start with the service engine, the SE.
Okay.
This is the definition of the data plane component. It's the part that, well, it does all the actual work.
The heavy lifting.
Exactly. If you need a simple analogy, think of the SEs as the distributed muscle, maybe the nervous system of the whole platform.
And that muscle works hard. I mean, the sources are clear. The SE's explicit role is processing all client-to-server traffic.
Everything.
When you talk about the core load balancing or the high-speed SSL termination, complex application acceleration.
That's the SE. That's its job.
And the flexibility seems immense, too. It can run as a standard VM.
Or even on bare metal.
Right. Which gives architects a lot of freedom in deployment.
It does.
Yeah.
So to contrast that, you have the Avi controller.
The brain.
The brain. Exactly. The centralized management and control plane. And what's absolutely crucial to understand here is that the controller never touches live client traffic.
Never.
Ever. It lives above the fray.
Okay, so if the SE is the workhorse, what's the controller busy doing?
It's a single point of administration. Configuration, policy, application. That's all controller territory.
Mm-hmm.
It collects all the analytics data coming back from the SEs, handles licensing, and it's responsible for pushing configurations out to all those distributed SEs.
Right.
And the fascinating part, the consequence of this separation is you get incredible performance isolation.
How so?
Well, think about it. If the controller needs a software update, maybe a patch,
Okay.
it doesn't directly impact the SEs that are currently serving, potentially millions of user requests.
Ah, okay. So the data plane keeps running uninterrupted.
Precisely. That's resiliency built right into the core design.
That architectural split sounds brilliant for scale, yeah. But once the components are deployed, we obviously have to tell the system how the application traffic should behave.
Right. We move from the sort of physical or virtual components to the logical configuration.
And this means defining two key objects. And administrators apparently confuse these quite often.
They do. And understanding the difference between the pool and the application profile is just essential, especially for logical setup and definitely during troubleshooting.
You mix them up.
You'll waste hours looking in completely the wrong place. It happens all the time.
Okay, so let's start with the pool. The pool object.
Right. The pool defines the set of backend servers, the actual servers ready to receive traffic.
So it's the where does the traffic go?
Exactly. And the key takeaway from the source material is that if you add a new backend server to your application, maybe you're scaling out.
Mm-hmm.
The pool object must be updated to include it.
Makes sense. The controller needs to know about it.
The pool handles that resource management piece. The list of available backend servers, the load balancing algorithm you want to use against them, like round-robin or least connections,
Okay.
and crucially, their health monitoring targets. The pool is constantly asking, is server A alive? Is server B responding? Yes or no?
Got it. So pool is servers, algorithms, health checks. What about the how?
Mm.
The application behavior.
Now that's the application profile. It
Mhm.
defines the actual protocol behavior, the application-specific setting.
Okay, give me an example.
Sure. Let's say your application requires session persistence. You need to make sure a user always hits the same backend server for their entire session.
Right, common requirement. Maybe based on a cookie or a header.
Exactly. Maybe you need to read a custom HTTP header value to maintain that persistence. You configure that specific behavioral rule enabling persistence, specifying the header within the application profile.
Of virtual service.
Correct. The profile dictates things like HTTP protocol settings, maybe TCP settings, those session persistence methods, request response timeouts, all that layer 7 stuff.
So this raises, yeah, an important point for any admin, right?
Absolutely. You have to internalize that behavior rules, like persistence or specific application timeouts, they live in the application profile.
While the list of servers and their health checks.
Live in the pool. They serve distinct but very interconnected purposes that govern the overall traffic flow. Getting that straight is fundamental.
Okay, so we've mapped the components, we've configured the logic with pools and profiles. Now let's talk operational resilience.
Yeah, keeping that application available during, say, necessary maintenance, or scaling up when traffic suddenly surges.
These are critical operational concerns.
And the platform is really designed around automation here. Nothing showcases that better than the upgrade process itself.
Right. Traditional load balancers often meant scheduled downtime for upgrades, didn't they?
Oh, absolutely. Planned outages were the norm. But here, we're talking about achieving high availability during the updates.
And the method used for the service engines, the SEs, is called non-disruptive upgrade, NDU.
That's the one, NDU.
Mm.
It's pretty much mandatory if you care about high availability.
And the process sounds quite elegant.
It is. The service engines upgrade one at a time. It's a rolling process. The controller manages it all.
So one SE goes offline, gets upgraded, comes back online, then the next one.
Essentially, yes.
Yeah.
But it's more like a replacement. A new upgraded SE instance might be spun up, traffic migrated, then the old one torn down. The key is users just don't see a blip.
Like changing a tire on a big rig while still rolling down the highway?
That's a great analogy, actually. The controller ensures traffic flow shifts seamlessly away from the SE being updated onto the others in the group, and then shifts it back once the upgraded SE is ready and verified. The result: continuous service, even during critical platform patching or upgrades.
That's impressive. Now, beyond planned maintenance, what about immediate incident response? A server fails, health monitor flags it. What happens?
The response is instantaneous, and it's automated by the SE itself.
Okay.
When that health monitor marks a backend server as down, the service engine immediately stops sending new client connections to that specific server.
Immediately stops new connections.
Right. It isolates the fault instantly, ensures new user requests aren't just thrown at a broken resource.
What about existing connections to that server?
Those are typically allowed to drain gracefully, finish their transaction if possible, but no new traffic goes there.
Okay, that makes sense. Fault isolation. And finally, let's talk about that moment. The unexpected traffic surge. You hit maximum capacity, you need more load balancing power, fast. What's the most efficient way to scale the load balancing resources themselves?
Yeah, this is where the platform's elasticity really shines. The most efficient approach leverages the controller's automation.
Hmm.
You generally don't go in and manually tweak settings on individual virtual services.
No. What do you do then?
Instead, you increase the number of service engines, the SEs, within the relevant service engine group.
You scale out the SE group itself.
Exactly. This dynamically adds more compute resources, more horsepower to the overall pool of capacity that all the virtual services in that group can draw from.
So the platform uses its inherent elasticity. You add muscle without reconfiguring every single service.
Precisely. It adds that capacity without needing manual reconfiguration of every VS you're running. It's much more scalable.
Okay, so if we kind of connect this to the bigger picture,
Yeah.
these mechanisms, the NDU, the automatic fault isolation, the elastic scaling via SE groups, they really highlight the platform's core idea, don't they?
They absolutely do. It's
Yeah.
all about minimizing manual intervention and maximizing automated availability across the entire lifecycle of the application delivery infrastructure.
Right. So automation handles the scaling, the upgrades. But administrators still have managed day-to-day services, right? Things still need attention.
Oh, yeah.
So when things do go wrong, or maybe just when proactive maintenance is needed, where should we focus our attention first?
Well, let's start with the one thing pretty much guaranteed to cause panic in any high-traffic environment.
Uh-oh. Expired certificates?
Bingo. That classic universal administrative headache.
That happens all the time.
It does. So, to ensure service is maintained, to avoid that completely preventable catastrophic outage, the primary operational task is renewing the SSL certificate on the virtual service.
Well before its expiration date.
Please, yes. Well before. Ignoring certificate rotation is just. It's a guaranteed service outage waiting to happen. Especially since, as we said, the SE handles all that SSL termination work. If the cert expires, traffic stops.
Okay, point taken. Stay on top of cert renewals. What about reactive troubleshooting? A user calls, the app is slow. Where do you start?
The immediate diagnostic tool, the admin's first stop, should always be the Virtual Services Analytics tab within the controller UI.
The Analytics tab. Why there specifically?
Because it's truly the single pane of truth. It consolidates just massive amounts of real-time data collected by all the SEs.
And processed by the controller.
Right. Our sources confirm it provides this comprehensive, really deep view of critical metrics. You don't just see slow, you see why it might be slow.
Like what kind of metrics?
Things like end-to-end timing, broken down into client latency, server response time, even application response time within the server, plus throughput, error rates, connection counts.
So you can quickly pinpoint the bottleneck. Is it the user's network, the trip across the internet, the load balancer itself, or the back-end server?
Exactly. Is latency high on the client side, or is the server taking ages to respond? The Analytics tab helps you differentiate that very quickly.
Okay, very useful. And one final detail on monitoring. Alert handling. What's the deal with alert actions?
Right. Alert actions are configured through the controller as well,
Mm-hmm.
but they have a very specific purpose. It's important to what they don't do.
Okay.
Alert action does not define the conditions that trigger the alert itself. That's done elsewhere, in alert configurations or health monitors.
Right.
And it also doesn't perform automated remediation actions like scaling up SEs automatically based on an alert.
So what does it do?
Its sole purpose is to specify the notification method. When an alert is triggered by some condition, where does the message go?
Ah, so like send an email, or an SNMP trap, or
Know.
call a webhook.
Precisely. It's purely about communication and notification, not defining the trigger condition or the automated response.
Yeah.
Just how you get told about it.
I want to leave you with one final thought to maybe explore on your own. When load balancing power can be added almost instantly, automatically, based on actual load, how might a centralized control plane-driven architecture like this fundamentally change the way traditional infrastructure teams plan?
Plan their budgets, plan their capacity.
Exactly. For those unexpected, massive traffic spikes, compare that to the legacy approach, right?
Right.
Which was often just over-provisioning expensive static hardware appliances just in case.
Yeah, buying big boxes hoping you size them right for the next 3 years.
Right, that fundamental shift in planning, moving from static over-provisioning to dynamic, on-demand elasticity. That's arguably where the real business value of this kind of architecture truly lies. Something to think about.